Welcome to MSB Technology. My name is Daniel Francis, and today I'm joined by
Jonathan Goldman.
We are the co-owners of MSB Technology along with Dustin Szymanski, and today we'd like to give you a tour from the front door into the factory and show you how we make our products, DACs and amplifiers, and we'll walk through production, machine shop, SMT, and then end up in the sound room where we can discuss the Sentinel DAC. So being in California, our spaces are very compact and every square foot gets used. So right inside the door, instead of a big lobby, we have purchasing department. So Janessa, who works here, does all of the kit purchasing for our products. So you'll see a lot of these blue bins that will have labels on them. The way the kits are put together is all the part ordering is done before the circuit board is ordered, and then it's moved to a kit cart that you can see here. And then we order the circuit boards, and then they arrive, and that becomes a complete kit. The reason we have the delay in ordering the circuit boards is, as a small company, we can adjust the circuit boards as the design changes or make improvements as we need to and implement them readily in each production. So this office here is my office as the mechanical engineer and designer. It's where a lot of the design work takes place, where we photograph products and create media for the website, so come on in. So this is my desk here, and right now you can see I'm working on the Sentinel DAC. So this is the solids modeling software we use. So right now we're finalizing this badge in the front of the Sentinel DAC here. So this is a stainless accent that we're refining and prototyping. And later we'll get to see that actually in the chassis itself, as it just came off the machine about an hour ago. And then behind you here we have Kevin Turnquist. He's our media manager. He does all of the website, photography, and video work for us. The other side here we have the machine station. This is where Jonathan Sondriel does all of the programming and actually makes the solids models I make into physical reality. So what you can see here is, again, the Sentinel badge that we're working on. So this is all the G code that will be used to machine out the Sentinel badge. And then in this area is where we do our photography and video work. So this is our test system on this side, where we do demonstrations and how-tos. It allows us to get real-life examples for customers and make it easier to instruct people on how to set up their systems. And you might notice this right here is a prototype Sentinel director, digital director. So not the final design, but this is one of the pieces that we made earlier on and kind of have been living with it, getting a feel for it. For me as a designer, it's very important to be able to be around my designs and find areas that I might want to improve or change as I actually live with it. Because that first impression is one thing, but like living with a design really allows you to come back and make the fine-tuned improvements that bring it that extra 10%. And then on this side, we have our photography studio. So this is where all of our website images and product photography is done. One of the things, again, as the designer, is it's really helpful to get real-life photos of products to see how they look, you know, from a photographic perspective, which is something that we care about. So it's important for us to take our products in-house through all these different stages as we develop them. So even a prototype like the Director, we've put out and taken photos of just to see how it comes across in the digital space. All right, so now we will move on to production. So this is our production facility. This is where we put all of our electrical and mechanical components together. So everything in this department is finished products. Not assembled, but finished. So we're not doing any of the dirtier work in manufacturing. So in these shelves we have circuit boards and chassis, base metal, jack panels, transformers, and all the materials we need to assemble orders. All of our orders are usually built when the order is placed. So we build in a batch depending on the configuration that's been ordered. But it's all sub-assembly based. So we have a lot of smaller modular individual units that get tested thoroughly before they go into inventory, and when they get assembled they get tested again, and then when they ship, they get tested a final time. So we put in a lot of checks to find any potential issues or problems before it comes up in the finished good. The last thing you want when building product is to build a finished product and then find an issue and then have to take it all apart, because that risks damage, wear, and it also risks a compromise in quality where you say, oh, it's almost perfect and we've done a lot of work, we'll let it go out the door, and that's not something we ever want to do. So we really make sure everything is up to our standard before it gets to the finished good. So come on into the production aisle here. The way our production works is we bring out a chassis for a subassembly. So this is a Cascade digital director. And then we'll bring out the circuit boards. And all of the hardware that we need to assemble them is all stored right here in each station. So this is for power bases and this is for DACs. So we try to prioritize the hardware so that it's very accessible, very efficient in the assembly. So one of the lean manufacturing principles is to reduce waste, and movement is considered waste. So if you're trying to build a product, we don't want you to have to go to a different desk to grab some hardware. We don't want you to have to go somewhere else. We want everything you need to be accessible and ready to use. Speaking of lean, we have all the tools needed to assemble our products in a single array. These are all torque drivers with specific torques for specific hardware. So again, when you're reaching for tools, we don't want you to have to find anything specialty or use the wrong tool for the job. So if the right tool is available, it's the easiest to use. All of the parts that we use are stored in bins above here for smaller assemblies. But in our production shelves is where we store our larger components. And we use what's called a Kanban system. So this is a simple mechanical inventory system where we have dedicated bins for production and then dedicated bins for reserve. So in here you'll notice some blue bins and some red bins. The red bins are our standard production. So if we get a new order, we're going to pull it out of the red bin. And as we work through this inventory, when we get to one of these blue bins, we trigger Kanban. So this QR code, when you reach this bin, will get scanned. And that QR code will send an email to our purchasing department to say, this product is ready to reorder. It'll say, this is how many we need to order, this is how many we have in stock that's left, and this is how much time we have to get it done. So it's a very efficient way for inventory. Again, efficiency is very important to us because we don't have to count this. You just look and you know if you have enough in inventory. If this is in the blue bin, if you see pieces missing, you know we should be reordering it. All of our systems are designed to be as fail-proof as possible, and this is just one of those methods. So on this side, you'll see a bunch of 3D printed bins. So these are, again, designed for very efficient space usage. So this is the Cascade foot. This protects all the parts from each other and stores them in very high density. It also allows us to keep an exact count. So we have 28 feet in this bin, and we know that. And you can look and you can see if there's any missing or not. There's no question about that. And as we work through this, you'll see, again, we have these blue Kanban bins. So when these foot puck inserts are gone, and you get to the next one, again, we have that QR code that says, trigger the next production. And this is enough stock to last us while we work on that. So when the product is assembled, we then take it to the testing station. So let's head that way. So this is Mario. He's been with the company for many years now. And he does all of the testing for MSP products. So he'll be doing subassembly, DAC module, all of the individual components will come through in productions and get tested here. And then final finished product will be tested here as well. So right now, he is testing a BDT update for this analog converter and running it through the Audio Precision. And I'll let Jonathan talk a little bit about that.
Yes, so we use the Audio Precision here. This is the 515. We use it to measure all of our modules, all of our finished units and subassemblies. We actually have 2 in the building. The funny thing about the Audio Precision and our equipment is actually more precise than the Audio Precision, because we have to have two different versions of every test, one for the production Audio Precision and one for the engineering Audio Precision. But as Daniel mentioned, everything is automatically measured. It's running through a DAC or a test right now. It measures hundreds of parameters of every DAC. And we have a program for the finished unit and a program for every subassembly. So as boring as it is, when we do a production run of XLR digital inputs, there is a specific Audio Precision test that measures the word sync out, the performance of it, and all the different sample rates for each one. So each one gets tested individually, and then it gets tested again as a final assembly here with the Audio Precision. In our test equipment, we have a special unit we made that gives us every digital output interface, and analog out. So we can check our Pro ISL, we have a word sync, Toslink, coaxial, AES output, and analog output. So it's all available for us to test for both analog outs and digital outs, and analog in and digital ins. So that's what we do here. And when it's time to test DAC modules, the DAC modules we produce many hundreds at a time. Each module is measured as an individual, not as a set. So we'll measure each DAC module to make sure it operates to our standards. And then when you put them together as a set, they always end up measuring better. And then, so from here, we can go over to the SMT department. Oh, sorry, we're going to go this way to shipping.
So after testing is complete, it comes to the shipping bench. So what we have here is very bright, full spectrum lighting so that we can do very thorough inspections. You can only inspect as good as the lighting that you use for those inspections, so it's very important to us to have very visible and clear light for that process. So on these, this is a Cascade DAC coming together. So Rob here is going to do all of the testing and the packaging material preparation. All of this will be done, cleaned, and ready for a personal inspection by either Jonathan or I. And we as owners take pride in inspecting every DAC that ships from the factory. So if you look on the box, you'll see a signature, initials from either Jonathan or I on every product going out, because we want to take that personal responsibility to show that we have approved what is going out the door. So here you go. This is the labels. So it has Mario's initials for testing, and won't be signed by Jonathan or I until we've taken a full look at the chassis and ensured it's up to our quality. So now we're going to start to take a look at the manufacturing side, not just the assembly of the circuit boards and of the machined products. So for that, we'll head over to the SMT department.
So this is our SMT department here. It's a very compact layout because we only need to use equipment as a batch machine. Typically we would have it in one long line. We just don't have the space to do that here. So everything's set up as a batch. The first step of this process starts with our drying cabinet. We use this to dry all the circuit boards and all the components before we do any assembly. It just assures the highest quality. As you can see, this is less than 1% relative humidity inside this cabinet. And then when we get the parts in, we actually turn it up to 38 degrees Celsius and run the boards at 38 degrees Celsius, 0.5% humidity to dry everything out. The reason why you need to get the moisture out of the parts is that when it goes through the rest of the process, if there's water captured inside the part, it will expand and steam and risk damaging the parts. Over here, this is feeder storage for a pick and place machine. I'll let you see what one of them looks like before you can see it in operation. So these hold the individual components that go in the pick and place machine you're about to see. So over here is the first step of the machine or the process. This is a stencil printer. What this does is, if you look in here, you can see some gray paste. It'll actually squeegee that through the stencil and put it on the circuit board. The unique thing about this machine, though, is it does full 3D inspection of the solder paste. So it has a LiDAR scanner, and it scans the board, puts the solder paste on, scans the board again, and it'll show you the results here. So we can go ahead and run a board into it now. So this is the board before it goes in. You can see all the gold pads. All the gold pads are where the solder needs to go. So we're gonna feed it in. And then if you watch through the window here, you can see it's going to go through, it's going to scan the board, it's going to print, and then scan the board again. The majority of errors in electronic assembly in all industries can be traced to this process. This is why it's so important for the 3D inspection of the paste, because if there's insufficient solder on a joint, you might not catch it until after the product's already been shipped. Whereas this will tell us if there's not enough solder, even on one joint, it will flag it as an error. So it just scanned it, now it took the board up, now it's pushing the paste through the apertures. This process is also sensitive to temperature and humidity, so it has a cooling unit to maintain the temperature and humidity of the machine. So as you can see, the holes are now all filled with the paste, and now it just pulled the board away. Now it's going to go through and it's going to scan the board again. Since there were no errors, it just stuck the board out. If it had an error, it would come up with an error message and let you see the solder paste on each one. So
yeah, that'd be great. Just do a swap.
Here's the board after it's gone through the printing. As you can see, all the gold pads are now covered with the gray solder paste. The next step it does is, this is the pick and place machine.
Don't bother that.
This is the machine that picks up the individual components, inspects them, and then places the parts down.
Speed hold it, turn the coolant on.
Yeah, and then even open the door. Just
so as soon as this board goes in,
like just pausing it here would be great.
We will start building this
open
board.
It, show what's getting done.
I'll get it on. So you have the table at like a 45 or.
This window down here is
this
clear,
is great.
It's easier to look through.
We're going to line horizontal and mill, you know.
We don't need to watch it, and I can show you the next step. So after this, the board will actually come out here where we give it a quick visual inspection. And then it comes over to our vapor phase reflow oven. So this machine is very cool. As you can see, the board goes in just like this. We can actually stick 2 panels or more in here. So right now the parts are placed in the board, but they're not soldered. They're just sitting in the solder paste. So this machine is very cool because what it does is it solders all the solder joints in a controlled fashion in an oxygen inert environment. So I'm going to go ahead and tell it to start, and if you look through the window in the top, you'll see what it does is it opens up a cover, and it will lower this board into a pool of basically Galvin steam. So there it is opening, and then you'll see the board's going to drop down. And this process can take about 10 minutes, but what it's doing is it's lowering it into like a steam bath instead of a hot air reflow oven. So the big parts and the small parts all will heat up at the same rate, and they will all reach the point what's called liquidus at the same time. So it'll just sit there for about 10 minutes. It goes through a temperature curve profile to maintain the correct temperature curve for each component. And so when this process is done, the next thing to do is final inspection over here. So the boards all get a full inspection by our inspection machine here. Every board has a QR code on it, so we can trace it. So if there's ever an issue, we can look it up, see if the machine caught it, see what parts it was built with. So the board goes in here, it gets sucked in, and then you can see it's going through and taking a whole bunch of pictures. And if you look on the inside, you can see it's flashing a bunch of different lights and colors. If there's an error, it'll pop up with an error message on the review station. But what I'm going to do is I'm going to stop it before the end so you can see all the parameters of what it's actually inspecting. So right now it says it's all good, but I'm going to stop it anyways. So as you can see here, we'll just pick like a capacitor as an example. Well, let's pick a different one. So here, what it's doing is it's measuring the size of it to make sure it's the correct size part. It's checking to see if the part is rotated, and it is not. It's checking to make sure it's sitting flat. So it's measuring the coplanarity. And as you can see, it sees a difference of 11 micrometers, which is incredibly flat. It's checking the leads, and here, as you can see, it's mapped out the curvature of the solder.
I still haven't even seen
So
it.
this is what's called, there's different failures, but one of the failures is called a head in pillow. If the solder doesn't bond to the component, instead of it being this beautiful curve here, it'll be a dome. And so what it's looking for is the curve to the part, because if it's a dome, it means the solder didn't bond to the component. When you have a failure like that, it can pass all your functionality testing,
So
and it might stop
crazy.
working in 6 months or a year, because it's touching, it's just not bonded. So it's like a bad weld joint. And for other components, it measures the leads, it reads the part numbers. Let's see if I can find the part number. No. So this one here, it goes through. It actually is reading the text of the part to make sure it is the correct component. It's the correct version of it. It checks for the color of the part. It also goes through and it measures all these leads. So as you can see here,
But if we could open it,
we
let
can
them
have
go
it
and
look,
at the chamber,
and you
that'd be
can
cool.
see the pins are all the same height. If one of the pins is bent, one of these spikes will be taller, and it'll flag it and say, hey, there's something not right here. Or if the part is shifted or skewed, it will show up in this graph. As you can see, the resolution of this is insane. Basically, if there's an error, it's not going to get through this process because it's checking not hundreds, but it's checking thousands of parameters. Every pin is checked for solder. Every pin is checked to see if it's flat. Every part number is read. Every capacitor is checked for the size and even the color, so it'll tell if there's a different color part in here. So this is an incredibly important process. Not only does it assure that we're using the right components, but if it does start coming up with errors, then we go back to this machine and say, why are we getting errors? Typically, it's something to do with the stencil process. Like if it says there's not enough solder, then we go back to this machine. Or it says, hey, this part number is different. Then we go to this and go, maybe a feeder is wrong. Because as you can see in these feeders, each one of these holes is an individual component. And you can see it could be easy to get one mixed up. So this is passed, so we will let it continue on its way, and out it comes. At this point, the surface mount part of the assembly is done. From here, it goes over to our selective solder machine, which is behind us, so we can go around. This machine is our selective solder machine. It was running earlier today, but it's finished its work for the day. That's the surface mount parts. This machine here solders all our through-hole components. So the through-hole components are the parts with wires on them that pass through the board. And as you can see on this, it goes through and it solders all the pins. Typically, you would use what's called a wave solder machine, which is a big wave of solder that you just pass the whole board over. The problem with that is it covers the whole board with solder, it makes the board get incredibly hot, and also it doesn't allow for double-sided assembly. So like if we have a connector on the bottom, we can't use a wave solder machine because it would wash all the surface mount parts off. This machine does it one pin at a time, or it'll drag it across. It's programmable. And I'll show you the inside in a second. But the advantage of this over hand work is it gives you very, very consistent soldering. Each pin gets, soldered for the exact same amount of time every time. It doesn't forget to do a pin, it doesn't forget to do a row, because it runs a program and it makes a very consistent and reliable output. All of our equipment here is designed for very high production, but we don't need to produce 10,000 boards. We have it because it's very precise. It's a quality first production line. So everything we have is quality, 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 not speed. The pick and place machine can do like 19,000 parts an hour. We don't need that speed. It takes more time to load it than it does to run it. To give you an idea of the selective solder machine, as we can look on the inside. So it's a little messy, it's still hot, so please don't touch. This is the nozzle. The nozzle goes in right here, and it shoots a little jet of solder out of it. It takes this nozzle up to each pin and solders it one pin at a time. The other advantage of this is the solder is at a fixed temperature. Whereas when you do hand soldering, your soldering iron is typically like 100 to 200 degrees hotter than it needs to be, because you're trying to get the heat in as quickly as you can. In here, the solder is at the optimal temperature for it to flow, which means when you solder, you're not stressing the parts or stressing the circuit board. So not only is it faster, it is also higher quality and less stress on the components.
So lathes are used to make round parts. So this will include buttons, knobs, and feet. So here, as for example, is the stock material we're cutting it out of, which is just stainless round rod. And there is the foot for Premier and Discretes. So this lathe here is fully automated. So we use robotics to unload, wash, and dry parts, and then store them in these trays. So some of the benefits of this kind of automation is it takes away some of the worst work you can have in a machine shop. So typically you'd have to stand here and wait 5 minutes, open the door, pull the part out, blow it off, wash it, clean it, put it away. But what this robot does is it does it all automatically. It does it reliably, consistently. It does it after hours, overnight, and it doesn't damage parts. It doesn't drop parts, and it also is able to pull them out and organize them in order so we can keep track of a production as it comes along. So say if we get to slot number 8 and we find an error, we know that everything before it is good and everything after it might have that error. So oftentimes when we're running over 100 parts, like 100 buttons, it's really nice to be able to just walk in and find where the tool might have worn too much and the tolerance is out of spec, and be able to differentiate that really quickly. We'll try to open this up for you after we do another part change and kind of show you inside what this looks like. But we do a lot of machining and automation to make the parts as versatile as possible. So what we like to do is we like to add features through machining to add value instead of adding handwork. This requires higher skill programming and higher skill labor, but the result is very valuable.
This is our engineering office. This is Dustin's office and my office. We've actually, I just realized last week, been sharing an office for 18 years now. So we've been sitting this far apart for 18 years, so he's basically another brother at this point.
I was an engineer for the company at the time, and he came back from
university
with his engineering degree, and he came right to work for the company.
Yeah. So I do more of the user interface of the product, the USB input, the dealing with the render, and then Dustin is the chief designer. He does all the audio critical component and software development. So his specialty is the clocks, the digital filtering, the DAC modules, the analog, basically everything that makes the sound what it is. We do obviously bounce ideas off of each other a fair bit. So in here, he has his Audio Precision, one of the world's greatest phase noise measurement systems for measuring clock jitter, and some other specialty tools. Over here is just our engineering prototype bench for playing around. And there's always at least 4 different projects going on in here at any given time. He's working on Sentinel development. We have some servers here for testing of ProASL output. Here's a really old Sentinel prototype, much older than what you'll see in there. Lots of things are always happening, so it's kind of a controlled chaos for us. And then in here, this is our listening room directly attached to our office, which has been amazing to have because it allows us to listen to our results in taking 10 steps. I'll tell you a little bit about this room. This room is unique because we moved to this facility about 3 or 4 years ago, and we wanted to build a space. So we found a building that allowed us to make the ceiling go taller, but more importantly, this is a soundproof room. So this is a freestanding room, completely enclosed and not touching the outside walls in any way. So you can be in here listening as loud as you want. And this has happened. I've come in and sat down and worked for 2 hours at my desk, and then somebody walks out of here, and I didn't even know they were here listening because the sound deadening. We have 2 layers, the thick drywall, we have the special glue, then we have a sealed outside shell cavity, floating walls, a soundproof door on curved hinges, so when you close it, it drops down and seals on the bottom. And then this is a door to the outside. It's a double door with an acoustical fabric over it. The room treatment, we actually hired an acoustical engineer to design it. We wanted a space that was best for R&D purposes. So we wanted something that was very almost analytical, but still something you can listen to. We weren't going for a showroom environment. Normally you would hide all this and you wouldn't have this much, but this was an R&D space. We needed a space where we could bring in, different speakers to try our amplifiers with. We have Eslons, the Forzas here. We also have Magico M2s, Magico S3s, Estalon X Diamonds, and then we also have in the back some custom speakers made by us for certain development tasks. So it's a very focused room for R&D. We keep our sources in the back here. They're connected to our DACs via our ProASL interface. In the wall, we have various power options. We have 120 volt and 220 volt. We have isolated power and non-isolated power. Even with the isolation, we're in a machine shop, a manufacturing facility. Our power here is worse than anywhere else in the world. We don't have a whole lot of audio tuning devices. In fact, we have none. And the reason is, if we're doing power supply development, we don't want to start with perfect power. We want to start with terrible power. So we can immediately hear the effect of power supply design and filtering. We're doing things to reduce noise and increase isolation. If you're in a perfect environment, you don't need any of it. But nowhere in the world is perfect anymore. So we leave it this way. We use standard power cords. We use our own interconnects, because if we make a change, we want the change to be very obvious to us. So we know our system very well. We can walk in and listen. If we change anything in any of the products, in the source, in the DAC design, the power supply design, we want the difference to be obvious to us.
Thank you guys for joining us today. We're very excited to share our facilities and kind of show you a behind the scenes look at what we do. We all love what we do, and we love coming to work every day. And If you can't tell from what you saw, this is a passion-driven company where we put all of our heart and all of our work at the highest standard to make the best possible products. So yes, very excited to share that with you, and we just hope you enjoyed the tour, and thank you for your time. So please enjoy. Thank you.
Thank you.
Thank you.